Okay, so today we are going to look at Fibonacci heaps. So you don't really need to know so much about binomial heaps to understand Fibonacci heaps. So I will directly get here. And anyway, you have the videos and the books to refer to, and if necessary, we will come back to binomial heaps later sometime. Okay? And much of what I'm going to do will be similar to what we did in binomial heaps, but there will be a lot of differences. So, in fact, Carmen's latest volume 3 directly talks about Fibonacci heaps. Okay, so let me just CLR is volume 3 has binomial heaps in exercises. Right? But they actually the description of Fibonacci heaps is independently given, and so if you so today's lecture will be somewhat like that. I felt it convenient to do binomial heap, so you get hang of this amortized complexity of some of these operations. But the earlier version, version 2 or 1, has whole chapter on binomial heaps. But today's lecture would be reasonably independent, so I think I'll directly get to Fibonacci heaps. So what we are going to do, one thing is that we're going to do amortized analysis. So I'm going to use the credit based method to do the amortized analysis. So every operation is going to come with some credits. And we will do some lazy thing, which is that, so what are the operations we wanted to support? We want to support insert, delete min, decrease key, and maybe also delete. But these are the things, for example, which was necessary for implementing Dijkstra's algorithm or Prim's shortest path algorithm. If you want to implement delete, I want to point to a node and say delete it. One way to do is to just decrease that value to minus infinity and do a delete min. Okay. So I'm not going to talk much about delete, but we will concentrate on these operations. So what we saw in binomial heaps is that you can do all of this like in binary heap, all of them in logarithmic worst case time. And the only extra observation was that insert in binomial heap is constant amortized time because it has a flavor of incrementing a binary counter. Okay. Yeah. Okay. So let me just go over all these operations for Fibonacci heaps. It will have a slightly different flavor than what we did for binomial heap. So what are we going to do for insert into my heap? So what did we do in binomial heap? We created a B0 node with that element and then checked my queue and see is there another B0, then I merged them and then I continued, right. I'm not going to do any more merges. I'm just going to create a B0 and stop there. Okay. So create a single node with X. Some later operation will do some cleanup. Okay. But to facilitate that, I'm going to put a credit on that node. On that tree, which is basically a one node tree. So how much credit it should come with? It should 1 unit to create that node and 1 unit to put a credit on that node. So it comes with 2. So its amortized complexity is 2. Okay. So we will come up with this credit argument and we'll argue that whenever some operation needs more time, it has enough on the data structure it can use, and so things will work out. Okay. Yeah, let's do decrease key, which is one of the important things you want to do. So decrease key. So at any point of time, okay, what is the invariant? We have a collection of trees, each tree satisfying the min heap property. So let me write down this invariant. H is a collection of trees in the binomial heap. It was a collection of binomial trees, but now I'm going to do all kinds of cuts on the trees, so it's no longer binomial trees, but some collection of trees. Each, values on the nodes satisfy min heap property. And then a pointer to the root containing min. So this is the invariant we maintain. Right? The collection of trees and within values on the nodes, and within in each tree they have satisfied the min heap property. The parent is smaller than or equal to the children. That's the min heap property, and you know that one of the roots is having the overall minimum in the entire set, and we will remember that as well. So now when I want to do a decrease key operation, what is this? So you have a collection of trees, and the decrease key operation tells you here is a node, change it from x to y, right? Because as I said, whenever you are performing this delete or decrease key operation, you have to tell me which node the value is and what change I need to do. So in the binomial heap, what did we do? We just use the fact that the height of the tree is log n. So we just checked, there are more things going on below. It's not just a leaf. That when I change the value, some min heap property may be violated, and by doing some swaps, we fix them, and the time was proportional to the height of the tree. It was all log n. It worked fine. Okay, but we don't want to spend log n time here because our goal is to support decrease key in constant amortized time. So what we are going to do, and first we will do some sanity check. If y is larger than x, then we just say no, you wanted to decrease, so I'm not going to do it, whatever. So let's assume that really y is less than or equal to x, and if it's a min heap, if this value is smaller than its parent, then you don't have to do anything, you're done, right? No restructuring. So these are some simple sanity checks we'll do, and we'll worry about the case where this value which you're the y, the new value of this node, which is y, happens to be bigger than its parent, we're going to cut. Okay, so cut the subtree rooted at x, and form a new tree, add it to the collection. But yep.
At the subtree rooted at x, y is
Yeah. I mean, the complicated case, right? So if y is less than x, otherwise I don't have to do anything, and y is larger than its parent. Sorry, it's a, then we need to worry about it. Okay, fine. Yeah. If this is less than its parent, then there is a violation because the parent is supposed to be smaller. So what we'll do is we'll cut this tree, adjust this tree, I mean, there may be many other things we might have stored in the invariant which I am not mentioning. For example, for every node, you will store the degree of every. You will store every node, you will have a left pointer, right, not left pointer, right pointer, because the degree may be much larger. So you will have the children in some order, all these are some implementation details. So when I cut this tree, this whole thing with this new y gets added to my collection. Okay. And you have to adjust the degree of this vertex. For example, it will subtract 1 from its degree. You may have to adjust the min value of the entire thing, because if this is smaller than whatever its min was, then adjust the min with this. Okay, these are some constant time operations. But one thing I don't want to do is to do some arbitrary cuts on any of these trees for some reason, which we will see later. So okay, so first time, so let me just say first time, so if its parent is unmarked, mark it and stop. So this is the decrease key algorithm. So initially, let me add to the invariant, initially all nodes are unmarked. So what is this marking, right? I said I don't want arbitrary cuts on the trees, I want to be careful about it. So whenever I cut some node, then I mark its parent to indicate that it has lost one child. Okay, so that is this marking. So if the parent is unmarked, it has not lost any child, then I am going to mark it and then algorithm will stop. But if the parent was marked, then the algorithm decrease key is not done yet. So first time when some child is lost, I am going to add it to the collection. But if this was already marked, what does that mean? That it has in somewhere it has lost some child, right? This guy was made as a subtree. So at that point, so now this node has lost two children, it has lost this and this. So now I am going to cut this entire subtree without these two children and add it to its collection and mark its parent, right? If it was unmarked. If it was unmarked, I am going to mark its parent to indicate that I have lost one child. But if it was already marked, cut the subtree rooted at its parent, add it to the collection, continue, and in the worst case, you might go all the way, right? So actually, so instead of if, maybe I will say while the parent is marked, parent of this x which you deleted, and now x becomes parent of x, and you have this while, end while. Or it is a root. Sorry, it's supposed to, yeah. So this is all part of the while loop. So okay. So what's that? Yeah. And I should have written it after the while loop. That when you come out, my parent is unmarked, I'm the root, and then I just go and mark its parent and stop. Okay, so this is sort of a cascading cut. Okay, so let's just see some. Okay, the book has the entire pseudocode, so you can. So here is this tree. So what happens when I am deleting first time, when I am changing this value and decreasing it, then what we will do is we will cut this and add it to my collection, and I am going to mark this. Okay. Next time, maybe let's say this, maybe this one got changed to some decrease key thing, changed to something else. So I'm going to cut this, create to my collection, but now I notice my parent is marked, so it has lost 2 children. So I'm going to cut this tree, which is this, right, excluding this, and add it to my collection. And I'm going to mark its parent. And next time, and something like, if suppose by that time, if you had lost this child, it was already marked, then I'm going to cut the remaining subtree rooted at that, add it to my collection, and I'm going to continue this. Okay. And when will I stop? Either my parent was unmarked, then I will mark it and stop, right? With the while loop, you will get out. If your parent is, if it is marked, you're going to continue. If it is unmarked, you will get out. Or it is root, then you will get out of this while loop, right? Yeah.
And the parent is marked. We cut the substituted of the parent, but do we create 2 separate subtrees?
Yes. So first thing is you cut this tree. You cut this tree and add it to the collection. Okay. Then you look at your parent, and if it was marked, then cut that tree also. Now that tree did not have this child, this subtree, because it is already made into a collection. Yeah. So why are we doing all this? We'll see later. But this is the entire decrease key operation. Okay. Now let's see how much credit decrease key operation should come with to pay for all these cascading cuts, right? So remember, notice that it's sort of, it has this amortized flavor, right? Because why should there be multiple cascading cuts? Because its parent has already lost a child, its parent has already lost a child, and so on. So maybe you can distribute this expensive cost to the guy who actually got deleted earlier, right? So there is a way to distribute, because this cascading cut won't happen otherwise. Initially it doesn't happen because nobody has lost any child. Gradually it happens as and when things, children are lost. So here is a suppose, so I claim it suffices for each decrease key operation to come with 4 credits. one more thing. Like what we did for insert, whenever I create a tree, I'm going to put a credit on that. Because somebody else later on will do some cleanup operation. For that, I need to put some credit on the tree. So the invariant on the credit I want to maintain is that every tree has a credit. Okay. So the decrease key operation, which is creating all these new trees, they make sure they come with enough to pay for some credit on that each of these new trees it's creating as well. Okay. And I claim that these 4 credits are enough. 4 credits, each one comes with 4 credits, and that's enough. Okay. So let's see, the first decrease key operation comes. What do? You cut it. I mean, of course, we'll assume that all of them are in this condition, because otherwise life is easy anyway. Right? So you'll do a cut. So you use 1 unit to pay for that cut operation, and then you put a credit on that tree, right? So that's 2 units, and that's all. So you actually have extra 2 units. What do you want to do? Put both on the parent. Okay, it's a natural, because parent is the one who's going to pay for it later on. So put the remaining. So the initial guys are cheap, right? So I'm going to give 4 credits. Put 2 on the parent. Okay, good. So this guy is cut, and so I use 1 unit to pay for the cutting of this operation. And I'm going to add, this thing has become a thing, so I put 1 credit there, and there is 2, so I'm going to put 2 on the parent. Okay. Now the next cut comes. I mean, if next cut happens somewhere else, it doesn't matter, it's the same thing, right? The next cut happens here. This guy also comes with 4 units, 1 to pay for this cutting, 1 to pay for a credit on that tree. It also has extra 2, which he will give it to the parent, so parent gets 4. Hey, once he gets 4, you can deal with something, right? So what do? You cut your subtree, give 1 on that tree, you have 2, give it to your parent. If your parent was already marked, then it must have already 2 credits. So you give this 2, it gets 4, parent is happy, continue this, and this thing works, right? So what is the invariant? So the potential function on this thing of my heap, can you tell me what it is? What is the amount of credit in the forest? Plus the number of trees, right? Because remember, every tree has a credit. So twice the number of marked nodes plus number of trees. So insert operation. So we can, what is the amortized complexity of any operation? We've seen that it's actual cost plus the potential difference. Insert operation, the actual cost is 1. What happens to the potential difference? What happens to the potential if this is the potential? What increases? Increases by how much? 1. Because the number of trees increases by 1, nothing is marked. So it's 1 plus 1, 2 for insert, right? Actual cost is 1 and the potential increase is 1. So the amortized cost is 2. That's why they come with 2 credits. For decrease key, well, the actual cost varies because there may be a lot of cascading cut it's doing. Suppose it's doing some L such cuts. Then what happens to the potential? Well, the number of marked nodes decreases by that much, right? Because these guys now become unmarked. So there is a 2L drop. But number of trees increases by L. So you have to pay, that there is a 2L drop, there is an L increase, and the actual cost is L. So everything cancels out. Okay, it's not L but L minus 1, and that's why it will, if you do the calculation, it will be like 4. Okay, so now Now let's do delete min, right? So decrease key has constant amortize, insert has constant amortize time. Now let's see how to do delete min. Okay? This is the potential. So you can see that decrease key in the worst case can be pretty bad. It can be as bad as the height of the tree, because you can just go up and up and up, and we really have no control on the height. It's not even log n. We'll see. But I don't care. I care only about the amortized cost, and that's constant. Okay, so hopefully with the credit argument is clear, but otherwise you can prove that amortized cost of insert is actual cost for any of them, any of these operations, plus the potential difference. So actual cost is 1 and the potential increase is 1, and the amortized cost of decrease key, if it is doing some L many cuts, then the actual cost is L, and the potential difference would be L minus 1 nodes, so have become unmarked. So this 2 into marked nodes have come down so much, but the number of trees has become L minus 1, and you have marked one extra node, because you finally, when you come out of it, you would mark your parent and you have to put some 2 credits on that. So if you do all these calculations, this 2L will cancel out. Yeah, so this is like 4. Okay, so this is the actual cost. This is the potential drop as L minus 1 nodes become unmarked. This is extra L minus 1 trees, and this is one new marked node. Now delete min is going to be the expensive operation. So what are you going to do? You have a pointer to the root containing the min. You're going to delete that. First thing is you have to find the min among its children, and then compare it with the min of everybody else in your forest. So it's sort of an expensive work. So if somebody is doing a lot of work, we'll give them all the work. So we'll give delete min the job of cleaning up the entire forest in a way that there is at most one tree of any particular degree, right? Like we did for in binomial heap, we ensured that there is at most one bi of every I, and bi, the degree of bi was I, right? So you're going to use the degree as a loose analog here. So what will delete min do? So delete the node containing the min. Add all its subtree to the collection. There is at most one tree by linking trees. And find the min among the roots. So delete min is going to do exactly what it's supposed to do. So there are this many trees here. So what we'll, and there is a pointer which says this is the min. So what I'll do, I'll delete this node, and these subtrees, I'll add it to my collection, find the min among all the roots, and because I need to know the new min. And now I do one more thing, which it's okay to do this without any extra cost. I'm going to do it. I'll tell you why. So what I'm going to do now, run through my entire collection and make sure. So if there are two nodes with degree 2, two trees with the roots having same degree, then I will link them by the way we were doing in binomial tree, by just making the smaller valued node the root, the parent of the other guy. Okay. So at the end of it, now you'll have this nice collection with at most one of any degree in this final collection. Okay. There are a number of properties we used about binomial trees, and height is at most log n, number of trees is log n. All that we are not going to use because they may no longer be true because because of all the cuts this decrease key operation is doing. But we'll analyze the cost and then argue that it's actually under control. Okay, let's analyze the cost. And how much credit should delete min come with, right? To pay for the entire operation, how much credit should it come with? Well, just deleting the node, some 1 unit here. So I'm going to add all its subtrees to the collection, right? And by the invariant we are maintaining each one of this should have a credit, right? So the time, the amount of credit I should have is the number of its children. Okay, let's call it, max degree. So in your entire Fibonacci heap, for any node, let's on Fibonacci heap on n nodes, let's look at let's call d of n as the max degree. I mean, earlier we were very happy, we said it was all log n in binomial heap, but we need to argue this now. So let's say it's d of n. You're finding the min among the roots to store the min. So okay, maybe that's why we should do this first. So now I'm going to do this linking. Okay, so I now run through my entire forest, and whenever I have two of the same degree, I'm going to link. And how do I pay for it? They have credit on it, use that to pay for it. Right? Every tree now has a credit. So I use that to pay for this comparison and linking. Okay, so this is free. Delete min doesn't have to come with that. Okay. Yeah. Yeah. But how many trees will there be at the end? So how many trees? Dn, right? At most one for any degree. If the max degree is dn, then after, so here this use the credit on the trees to pay for this. Now I have ensured that there is at most one of every degree. So the number of trees at the end would be at most some dn of them. I need a credit on each one of them, so I need some dn more credits. Okay. And I'm going to find the min among the roots. Number of such roots is again dn. Finding the min, so another dn. So overall, the credit I should come with is some order dn. Right. So I'm done if I show that dn is log n, order log n. That and this is where all this carefully chosen cuts are going to be useful, because your tree at any point of time, I will argue that the maximum degree of any vertex in your Fibonacci heap is some order log n. Okay, so including for the roots or intermediate nodes, and hence the amortized cost for delete min would be order log n. Okay. So the claim what is dn? Max degree of any vertex. In fact, not necessarily even root. So this kind of thing will happen even in some other structures. If I want to find the new min, anyway delete min, if I have to find the new min, I have to find the min among my children, among other things. So anyway, I have to spend time proportional to the number of children I have, the degree, my degree. So I might as well do a lot of other things, without blowing up the time, and that's what we're doing here. Right, so here number of such trees at the end. So because you're going to put some credit on them. Okay. So now what do we have to show? If I show this, I'm done. I've ensured that insert and decrease key operations take constant amortized time, and delete min takes log n amortized time. All this is amortized time because we are talking about using this credit argument, right? Because in the worst case, in the entire, there may be as many as n trees, and you might be cleaning up all of it. So that's not what we're talking about. They're all being paid for some earlier operations. Okay, so all we have to do is the way we are doing these operations and look at any point of time at any node in your collection in your forest, the maximum degree, if the total number of nodes is n, the maximum degree is some order log n, and it's actually going to be more precisely, we will show its log n to the base phi, which is this golden ratio. Okay, and all we need is because of the, and this is where we are going to use the fact that I do this cuts very carefully. I never make, I make sure that nobody loses. In, if you have a tree at any point of time and you look at any node, from that it would have lost at most one child, because if it had lost two children, it would have become a root somewhere else. Okay, so here is this little lemma and this, and then we use some properties of Fibonacci numbers and it will complete the analysis. So let T be a tree in our heap, right? It's one of the trees with root. No, I don't even need. No. I don't, because I am not necessarily talking about a root. So let X be a node with degree I in one of the trees. It could be a root, it could be somewhere intermediate level, and let y1, y2, yi be its children in the order in which they became a child of X. Then degree of y1 is greater than or equal to 0. Degree of yes, this is the claim. Is the statement clear? So we are doing this all these inserts, decrease key, delete mins, and algorithm goes on. At some point, I stop and say, look at some tree and look at some node in the tree, and let's say that node has degree I. Then I'll look at y1, y2, yi. These are the children in the order in which they became a child of X, right? In the whole process of our operations, here was X. Y1 became the child first among these guys, and then y2, and then yi. Then I claim that in this current tree, my degree of y1 is at least 0, and degree of yi is at least I minus 2 for I greater than or equal to 2. Degree of y1 is greater than or equal to 0 is trivial, nothing, we are not saying anything. But let's look at y2 or some let's look at some intermediate node yj, j greater than or equal to 2, right? Why did it become a child of X? Let's look at our algorithm, the way we were doing things. When would we make one guy a child of the other? If the degrees are the same, right? that delete min operation will do it. Otherwise, we are cutting it, putting things, that's all we are doing. The only operation, in fact, insert just creates a node. The only operation that makes one guy a child of the other is the delete min operation, and it will do it when the two guys are the same degree. So, at the time this guy yj, so y1 to yj minus 1 are all even now. So, the degree of x, okay, so proof degree of y1 is greater than or equal to 0, nothing much. Consider yj j greater than or equal to 2. When yj became a child of x, degree of x must have been greater than or equal to j minus 1, right? Why greater than or equal to? Because maybe x might have lost somebody. But at least y1 to yj minus 1 are sitting here, they would have been there also, because I'm considering them in the order in which they became a child. So, yj became a child of x after these guys became child, and they are still here in the tree. So, degree of x must have been at least j minus 1, and yj became x. So, that means degree of yj would also be at least j minus 1, because only when the degrees are same you would have made one guy. Degree of yj then would be greater than or equal to j minus 1. Right, but x might have lost a child now later, because the way decrease key. So, it's j minus 1 or j, degree of x at that time. So, whatever the degree of x was, degree of yj would have been at least that much. It will be exactly equal, but I don't know what the degree of x was at that time. All I know is that's at least j minus 1. So, a degree of yj is at least j minus 1. That was then, but now it could have lost one child, because we never allow somebody to lose two children, because we would have moved it away and made it into the root. So, now as this is it. Now it's all, I mean, this is what we want to show. We will show. I'm going to erase this, but so this is the only crucial lemma where we are using the fact that in decrease key operation, I mean, delete min is the only one which is making one guy a child of the other, and if it does it only if the degrees are same, and decrease key operation never allows more than one child to be lost, because if it loses more than one, then this guy yj would not be here, it would have become a root of another tree. Okay, so we're going to use this lemma now. Okay, so what am I saying here? Your algorithm, I mean, proceeds by doing these inserts and decrease key and delete mins, and at some point I stop and I look at my forest and look at one tree and look at some node in the tree, and I want to claim this. If the node has degree I, and if y1, y2, yi are its children in the order in which they became a child of x, because y1 became child first, y2 child became child later, and so on, then the claim is this. That at this point in this tree, my degree is at least, but when I say degree, I mean the number of children. Okay, I'm not counting its parent. Okay, when I say degree is number of children. Degree of y1 is at least 0, and degree of yi for other guys is at least whatever I minus 2. I shouldn't be saying it yi because I has fixed meaning. Proof degree of y1 is greater than or equal to 0 is trivial because y1 is sitting there, and but consider any yj j greater than or equal to 2. At the time yj became a child of x. Why did it become a child of x? Yj's degree and x's degree were the same, and that's why delete min operation made this guy the child of x. Okay, so degree of at that point hence greater than or equal to j minus 1. Right? Degree of yj and degree of x were same at that time, but x had at least these children, so its degree was at least j minus 1, and these two guys have the same degree, so its degree would also be in j minus 1. And since then later on yj might have lost another child due to a decrease key operation, and so its degree would be at least j minus 2. Okay, so now to show that the degree is not large, right? What is our goal? I want to show that the degree is logarithmic, maximum degree is logarithmic. So the way I mean, how have we shown this, right? We've done this in AVL tree connecting height and the number of nodes. If the height is something, the number of nodes is very large, and hence height is logarithmic in the number of. In particular, we've shown that the number of nodes in an AVL tree with height h is exponential in h. So you can turn it around and say that if the AVL tree had n nodes, then the height would be logarithmic is in n. Okay, we're going to do something similar here. What is it? That if your degree is I, because of this property, the number of nodes will be exponential in I. So if the total number of nodes is n, then the degree will be logarithmic in n. Right. So the claim, okay, let Si minimum number of nodes in a tree, in a tree in our algorithm, right? What is this tree? Whatever tree we obtain through this process of insert, delete means and decrease key. Then we claim, okay, let's actually prove what we have. So then then from this, so the root has degree I, then we know that this guy has a degree at least 0, this is at least 1, this is at least 1, at least 2, and so on, right? Degree I minus 2. So Si is greater than or equal to, I'm counting the total number of nodes in this tree where the root has degree I, right? So let me count 1 for the root, 1 for this node, and then I'm going to say that this, yeah, this is my claim, it just follows from lemma. Right, this one is for the root, this is for the first child. Then I know that, so inductively, the number of nodes in this subtree, right, that's all I care about, I'm counting, right? What is the total number of nodes? It is 1 plus 1 plus the number of nodes in this subtree plus number of nodes in this subtree plus number of nodes in this subtree and so on, right? That's the total number of nodes in this tree. So this is 1 plus if you pick any particular j, since its degree from this lemma is at least j minus 2, the number of nodes is at least s j minus 2, sorry, not I, j. It's j equal to 2 to I, right? Now you should see some similarity to Fibonacci numbers here, and then that will. Okay, so the claim is that Si is greater than or equal to Fi minus 2, where this is the Fibonacci numbers. And since Fibonacci numbers are exponential, you'll see all this. But let's continue with the proof. Is the claim clear? So Si is what is the minimum number of nodes in a tree in our process where a node has degree I. Because of this lemma, this Si is at least 1 plus summation j to 2 to I Sj minus 2. And I claim that Si is at least Fi minus 2. Let's prove this by induction. Maybe I should define what is minus 1, minus 2, but let's say from okay, we'll come back to this. Let's look at some properties of Fibonacci numbers first. So let's write claim. This is what I wanted to write. Fi equal to 1 plus no, maybe yeah. 2 to I. Okay, maybe that's why. Okay, so we'll keep this for a moment. Let's remember this. This is all we need. Now I'm just going to just talk independently about Fibonacci numbers. Okay, so Fibonacci numbers, I claim this. Okay, so this proof by induction. F1 is 1 because this term is 0. F2 is 1 plus, what does it say? F0. Yeah, which is equal to 1, which is fine. Yeah. So I assume it's true up to some I at the induction step. So these are base. At the induction step, what do I have? Fi plus 1 by definition is Fi plus Fi minus 1. And from the induction hypothesis, I'm going to say this is 1 plus summation j equal to 2 to I minus 1 Fj minus 2. Replace the? So you bring this in, right? So then, replace the Fi with the summation, not Fi minus 1. Oh, Fi is what we assumed. Okay, fine. Okay. So this is Fi is 1 plus summation j equal to 2 to I plus Fi minus 1. Okay. So this goes all the way up to I minus 2, right? And I have I minus 1 also, so I can just do this, and that's exactly what I want. So okay, I mean, you may or may not have seen this, but it's just some interesting, nice property of Fibonacci numbers. Since they are again defined inductively, you can prove by induction. So for Fi, I've replaced it by this. Yeah. So I just somehow want to relate this with this. Okay, that's the goal. But before that, let's also get one more thing about Fibonacci numbers out of the way, and then we will. Where phi is this golden ratio, right? I think I want to see this. Yeah, what I wrote is not quite right, because if I put I equal to 1, F1 is 1, but this is phi which is more than 1. Okay, so I think this is what I want. So so how does Fibonacci numbers go? Let's write this, right? F0 is 0, 1, 1, 2, 3, 5 kind of thing. So again, proof by induction. When I equal to 0, we are talking about F2, which is greater than or equal to phi per 0, which is 1. F3 is 2, which is greater than or equal to phi. So assume true for small i's. Then I have Fi plus 3 is equal to Fi plus 2 plus Fi plus 1. So this is the induction step. which is greater than or equal to phi to the power I plus phi to the power I minus 1, which is equal to phi square into okay, and Fibonacci numbers satisfy one quadratic equation. What is that equation? Remember? It's basically they satisfy x square equal to x plus 1, right. So, phi plus 1 can be replaced by phi square. Okay, so these are some nice independent properties about Fibonacci numbers, can be proved by induction. Now, let us come back to our problem. What do I want to say? Yes, I know what I want to say. Is this clear? Simple induction and the fact that phi satisfies this equation. Okay, so now so not I minus 2, I actually want to say I plus 2. Right, this is the next claim, the final claim. So, all we needed was that one little lemma which said that if you have somebody with large degree, then its children also have large degree. That is all we used, right, where large is quantified by, if this is I, then the jth guy has degree at least j minus 2, okay, and that is achieved because of the way we were cutting things carefully in the decrease Q operation. So, now I claim that Si, if your node has degree I, the minimum number of nodes in that subtree rooted at I is greater than or equal to the I plus second Fibonacci number, which I know from this lemma is greater than or equal to phi to the I. So, why is this? We will prove by induction. Because of this claim, we know that Si is 2 plus summation j equal to 2 to I, right. So, this is for all I greater than or equal to 0. Base case, when I is 0, I have a node with degree 0, it has exactly one node in the subtree, and that is greater than or equal to f2, they are the same. So, assume for up to I minus 1, yeah, right. So, again by induction on I, base case S0, the minimum number of nodes in a subtree with degree, the root has 0 is 1, which is equal to f2. So, that is fine, and assume Si is greater than or equal to Fi plus 2 up to some I. Now, let us look at Si plus 1. From here, it is 2 plus summation j equal to 2 to I plus 1 Sj minus 2. By induction hypothesis, it is greater than or equal to 2 plus summation j equal to 2 to I plus 1. Sj minus 2 is greater than or equal to Fj. And then from this claim, it should follow, right. So this 2, I'm going to bring in 1, 1 here and start from F1. Yeah, okay, fine. Actually, I can go up from 0 because F0 is 0 anyway because of my convention. So this is going up to from F0 to I minus 2 to get I. So this is 0 to I plus 1, so I should get F I plus 3. So that somewhere it's greater than or equal to because of this. And that's what I wanted to show, because Si is greater than or equal to Fi plus 2 is what I wanted to show. I've assumed up to I, and for I plus 1 follows. Okay, so, and we know because of that is greater than or equal to. And final corollary, and then we wind up, is that max degree, which is d of n for any tree on n nodes, is at most log n to the base. Phi, why? Because you suppose you have a tree with degree I, then with all this claim, the number of nodes is at least so much. But you told me that the number of nodes is actually n, so n is smaller than this, which is less than or equal to this. And so now you take log n to the base phi I, you will get the degree is at most this much. Right? Because what we have is, if the degree is I, then the minimum number of nodes it will have is this, and this is your, but the tree has n nodes, right? So now you take, so this implies that I is at most log n to the base. Okay, so not very involved. I mean, some calculations. The important thing is to remember, something like this happens in an AVL tree where we say, you don't want to be completely balanced, but I allow a little bit of relaxation in the height. And the height becomes instead of log n to the base 2, it's log n to the base phi. So here also, this binomial heap sort of gives you some sort of a motivation to keep the heights and the degrees and so on, but somehow by, if my goal is to support decrease key fast, instead of running it over into the tree, we'll do some cutting, but we do this cutting very carefully so that the degree of any node doesn't blow up too much. Okay, so bottom line, we have this Fibonacci heap where you can do insert and decrease key operations in constant amortized time. But delete operations, whether it's delete min or deleting an arbitrary element, have a log n amortized time. Okay. In the worst case, delete may actually take linear time, unlike binary heap. But that was the point, right? We wanted to sacrifice worst case to gain amortized cost, because in the algorithms we apply these data structures, I don't care about one operation, I care about the sequence of operations. Okay, so this is whole thing is due to Fredman and Tarjan. So Tarjan was the one who pioneered this notion of amortized complexity, this way of analyzing credit and potential and all that. And they developed a lot of data structures, including Fibonacci heaps. So this is due to this. So I would credit and Friedman and Tarjan is this Fibonacci heap. But it's also said that this is not really good in practice because of all these complicated implementations and multiple degree pointers and so on. But in theory, they have this good performance. And there have been multiple alternatives to Fibonacci heaps discovered. There are papers as late as last year where you can say, okay, here is another way to do this, achieving the same complexity of Fibonacci heaps, but arguably simpler or simpler analysis or something. Okay, I think, okay, so we'll